All right, well, welcome everybody. I wanted to start today just going over some of the stuff that's going on next week. So you'll see, now you'll see posted on Moodle. I have a huge graphic novel without any graphics, so it's not actually exciting. I have a huge novel written about what's happening next week. I tried to kind of lay out, okay, so we really have three different things that are going to be coming next week. A quiz on Monday, there's some information about that, exactly what you can expect, what it's going to look like. The big thing to take note of for the quiz, and I'll blow it up, so that's this top, the top bullet. It's going to be a manometer problem. Okay, so I have 2 points because I'm bad at this. The second point, homework number 3, that will be your notes for the quiz. So I'm not going to give you equations, but you're going to have your homework solution. So the only one, right, homework 3 is not due Monday. Homework 3 is due on Wednesday. The first 2 problems are what the quiz is going to be like. So I guess take that for what you will. So those first 2 problems are going to be the ones that you want to make sure that you understand before launching into that quiz. And then you'll have that out. You can work with that out in front of you as you're taking the quiz. Okay, does that make sense? So I guess when you're doing the solution, make sure you have the equations written and you know what you're doing, and future you is able to interpret what past you was thinking. Okay, so that's going to be the quiz. The rest of the homework, which is the longer part, will be due on Wednesday. The kind of hiccup, I guess, with the timing of everything, that homework will be, I will post the solutions for that homework so you have them to study for the exam. So because of that, late homework gets a little more difficult. So normally I have late homework, if you turn it in a day late or something, it kind of decreases every few days. But because of this, because I'm releasing the solutions that day, the Wednesday is kind of a hard deadline for that. If you turn it in after Wednesday, it's worth 50%. So those are the 2, I guess, kind of different things. Like I said, I have this all written down here. And then I have some information about the exam itself. The biggest thing just to note, if you're going to be taking this remotely, I have to know about it so that we can do that. If you email me Friday at 11, hey, I want to take the exam remotely, that's going to be challenging. So if you're going to be remote, that's for some reason, let me know. We can plan that and we can schedule how best for you to take it. But ideally, let me know by Thursday so we can actually get that scheduled. You're going to be given a handout for the exam with some equations and unit conversions. That handout is posted here, so you can open up and look what that is beforehand. You're going to be allowed to use a homemade 1-page sheet of notes with equations and maybe an example problem or whatever else that you would want. The exam topics, it's going to be chapter 2 and 3, and really look back at the solutions for the homework sets, like homework 1, 2, and 3. So those are going to be good places to know what equations are going to come in and how we're going to use those. I guess one word of caution. So the book has, like all engineering books, they like to derive equations for specific cases. So when you're just going through the book, don't just be writing down equations from the book without context, especially for some of the statics stuff. Some of the equations that they derive could lead you astray, because therefore, if this is like, gravity is acting only in the z direction and the things are, then we can do this simplification and ta-da. But it only works in that specific case, right? So make sure you're, matching up the specific case to the specific problem, or just stick with the more general equation, right? That applies to a greater number of cases. But kind of however you do it, make sure on your note sheet that you're matching up like when I should actually use this equation. So it's going to be like some of the streamline type math stuff. So that was really the first two. It's mainly the first homework assignment, but it popped up on the second homework assignment too, looking at the velocity vector. So it could be some stuff like that, some of that math. It's going to have another manometer problem or something like that, some sort of fluid static seed problem, and then a force on a submerged surface problem. So those will be kind of the main problems on there. It'll be, I haven't made it yet, but it'll be probably like 3 or 4 problems. But you can for sure you'll find a viscosity problem, kind of like, maybe like what was on this last homework assignment. The first problem on this last homework assignment, which required you to like go back and do torque and do physics and stuff, I don't think that's a particularly good exam problem, just because it requires all this extra whatnot to figure out, okay, what's the velocity from the rotations and how do I, it requires extra whatnot that's not fluids. So there might be some of that, but probably not as much as that. There won't be as much as that problem. I think I like it as a homework problem, but not as an exam. That kind of makes sense. Are there any like general questions on exam or what's coming up the next week?
You can have 1 page from that.
Sure. Yeah, I don't particularly care. Yeah, I'm not, so yeah, I see that more as like a way for you to study than me trying to police exactly what you should have with you. Like this is, right, we're here to learn things. So making that as a way for you to be able to organize and categorize things and see what are the important concepts, like that's the reason that we do this, rather than everything like open book, open notes. I don't think you learn the information the same way as if you have to go through and organize and categorize. So exactly what that looks like, I don't particularly care. So do it in a way that helps you learn the material. Okay, sound good? All right. So we are going to wrap up with kind of things that we're not going to really talk about, but just some interesting observations from fluid statics. And then we'll move on to the next stuff. So things that we haven't talked about yet, and won't talk about in really any detail, but are just kind of a taste of some of the other interesting stuff that's out there. So one thing that you'll see, or just kind of, again, maybe to help us build like a mental intuition for how some of this stuff works. So this is, so our book has a whole lot of fun in chapter 3 doing curved surfaces, which is fine. So if you had something like this, right, if these are your axes, this is y, this is x. If you had some surface like this, right, that's your wall, and then that's water. it's interesting to say what kind of forces are actually acting on that curved section of wall. And our book says, oh, this is a fun time to do some more math and derivation stuff. Like we can say, okay, the equation for the wall is x squared plus y squared, and then we can go and integrate things, and it gets really excited about that. I'm less excited about that, because if you had to solve something like this, you would just like throw it in CAD and solve it in a couple minutes. But that, and I don't think that math really helps you build any intuition for looking at this and saying what kind of forces would be acting on that. So just the kind of the interesting part, at least to me, is yeah, trying to build this intuition a little bit. So if we look at this type of a problem, okay, we're actually going to get two resultant forces, right? There's maybe no surprise. There's going to be one. Did it die? Back. Okay, I won't touch it. So there are going to be two resultant forces, one in the x direction and one in the y direction. Still. Let me unplug and try again. You working? All right. So there are going to be two resultant forces, one in the y direction. Come on. Ta-da. I don't move. All right. Did it do it again?
It will turn off.
As soon as I stop looking at it. All right, so there's going to be one in the y direction, and there will be one in the x direction. And like I said, we could kind of, with the same approach, the same ideas that we used for a plane, we could find what is the magnitude of that force, what is the result, the final resultant force, where is that acting, what are the, like we could do all of that stuff. But just a useful, like, conceptual thing is to think of what we call the null fluid forces. So if you said, okay, so there's going to be that curved thing is holding back the water. So like another way to picture it is, what would it take? So that thing has to be exerting a force on the water to hold it back as it's doing. Another way to flip that is to say, what would it take to get to a place where that's not like holding the water back? So if we looked at a different picture, the same gate, I'm going to draw that better. Okay, so this same gate, y, x. So we have the water over here, but what if we had water on both sides of the gate? Then the water pushing from the right is going to be canceled out by the water from the left, because right, then it's not holding back anything because there's water on both sides, right? It's just like hanging out there in the water. So this tells us the forces, force to, and I'll put this in quotes, hold this back. Is equal to that water, and I guess right? Shade that in. So the idea is if you put water on both sides, then it would be fine. So what's the force required? Well, it's the water that's like currently on the left side. So the null system is the system with the missing fluid filled in. Right, and the missing fluid is the fluid which would balance the forces. Okay, so if you wanted to say what force does it take to hold that water back, the force required to the weight of the null fluid. So let me just draw that. So it would be like the weight of this fluid, that would be the force that the gate has to exert. Thanks. Does that kind of make sense conceptually? Like, because if fluid is filled in everywhere, then the system is the water's just sitting there. So if you take away some of the water, you have to replace it with a force equal to the part that you took away. Which I think is kind of a useful way to think about and frame something like that. So how much force do you actually need? You can kind of picture it as what fluid did I take away from the system? The weight of that is going to be the force that I need to kind of balance that out. So I think kind of a useful mental image to think about things that aren't just like plane walls and stuff. I think going through plane walls helps you picture a little bit like how does force and pressure relate and moment and some of that kind of stuff. But I think this is also a useful tool. Okay, the last part is, and I have to look at my notes because otherwise I can't spell. I don't know. For anybody else, is that the hardest word in English? Just me? Buoyancy? Buoyancy? Buoyancy. So buoyancy is another part of fluid statics. Again, we're not going to really cover it too much in depth, but we'll look at just some kind of interesting takeaways from it, so that you've at least seen it a little bit. So if you have an object, we'll draw it like this, which is underwater. There is going to be a force pushing, so this is, we'll call this water. It could be any fluid, it could be air, it doesn't matter. Okay, there's a force pushing down on the top surface of the water. We'll call it F1. And there is a force pushing up on the bottom of the water, F2. What are those forces from? They're from pressure. So this is P1A, and this is equal to P2A. We made it a rectangle because that makes life easy, but this will kind of all come out in the wash, and it doesn't matter if we could have chosen any shape we wanted. Okay, so what is the force of pressure at the top? That's equal to rho g h1. This A plus equals rho g h2a. So if you want to find the net force, which is caused like pushing up on the object, it's going to be the difference in those two forces. So the buoyant force call it F buoyancy, that's going to want to make that object float, is equal to F2 minus F1, which is equal to rho g H2 minus H1A. Where this guy here is the volume of the object. So a really nice, simple principle, FB equals rho G V, where the V with the cross in it, that's volume. I'll write it over here. That's the volume of our object, of our rectangle here. So if you want to know the net buoyant force, the force that's pushing up on the object, it's equal to rho G volume of the object. This is, this is the density of the fluid, and this is the volume of the object. Okay, so if you've heard of, I'm sure you have at some point, you've heard of like a big ship. People talk about the displacement. What they're talking about is the amount of water that it displaced. The volume of water that it displaced, that's the buoyant force that's pushing up on the ship, which if something's floating, that is equal to the force of gravity. So if you talk about the displacement, that's the weight of the ship. It's just measured in this method. This equation, this is an old one, super old. Does anybody know who the person was that this is named after?
Was his name Buoyant?
No, good guess. It is a good guess. It's somebody that I'm sure you've heard of. This is Archimedes. So this qualifies as the oldest equation that we're going to write in fluids. Did anybody hear the story of like Archimedes? There's the king, and Archimedes has to tell whether his crown is made of real gold or it's an alloy. So this is how he did this. Anyway, Archimedes' principle. So it's the buoyant force is equal to the weight of the displaced fluid. The other thing to just kind of general principle, FB acts at the centroid of the submerged area. So if you have something underwater, the resultant buoyant force, it's going to be up, and it's going to be like acting at this, it's going to have this magnitude, and it's going to be acting at the centroid of the underwater part. So let me just draw a couple pictures to explain what this is. And this also gets into, so let's say we have some water there. We have an object that, say it looks like this. Okay, this is our object. Okay, it's floating in the water, but it got tipped, right? So something, it's not floating. Normally, somebody tipped it. So the center of gravity is still there. It's a uniform density. So this is the force due to gravity. And if we were to say, what's the force, the buoyant force? It's acting up through the center, the centroid of the submerged area. So we just care about this part here that's underwater. And that would be the center of it. So I'm just going to kind of eyeball it because it's not easy. It's going to be somewhere there-ish. Does that seem reasonable? You can do better in your picture if you want. It's going to be just like, where is the center of that? And it's going to be acting straight up. So what type of, what's going to happen to this? So this thing is out of equilibrium, but what's going to happen as a result of those two forces? Right, force of gravity is pushing down, the force of buoyancy is pushing up. There's going to be a torque on the object, which is going to, so there's going to be a restoring, right? If you push down on it, it's going to tip and it's going to right itself. It's not going to flip over. If we had an object like this, say this is how it's floating. The center of gravity is there, pushing down, so that's Fg. Again, our buoyant force would be acting on the centroid of this submerged area. So that's going to be, draw it in blue again. That's going to be acting this way. And what's going to happen to our tall, skinny shape? It's going to have a torque which causes an instability. Right? It's not going to stay straight up. It's going to tip over on its side. So a couple notes. We have, right, G acts at the center of mass. FB acts at center centroid of submerged. The submerged shape or the submerged portion. And you can actually get, by looking at where those two things are, you can get a sense of, okay, if we took this object and if we tipped it a little bit, are those going to cause a restoring force or restoring torque that's going to make the thing stay upright? Or is it going to cause it to tip over the whole way? And you can use this to say, okay, how far would we have to tip it before it actually flips over? It's going to be where all of a sudden the force of gravity and the force of buoyancy, they're going to like keep coming closer and closer together, and they're going to cross each other, and then the thing's going to tip over. So generally, if something tips sideways, for something to be stable, we look at what's happening. If something is unstable, the center of buoyancy doesn't move that much as the thing tips. It stays pretty much in the center, but the center of gravity moves a lot, right? So the center of buoyancy is pretty much staying still. The center of gravity is moving. That's causing it to tip over. So it has like a high center of gravity would be another way to describe it. For something to be stable, the center of gravity pretty much stays the same, but as it tips, the center of buoyancy moves a lot to cause that restoring force. Yeah, Chris.
So for that case on the right, once it gets past a certain point, would it become stable then? Like,
then it would become stable on its side, yeah.
So every unstable torque eventually becomes stable.
It's going to have to become, yeah, it's going to become stable somewhere. It'll just be in a different orientation. So if you want to say, like, is this stable? This shape is stable on the, right, it's the same shape basically, but it's stable in the left orientation. It's not stable in the right orientation, as you know intuitively. But the reason is that as it's tipping, you can think about it with like what's happening to the center of buoyancy as it tips versus what's happening to the center of gravity. And those can cause either the thing to right or the thing to flip over. So if you're trying to design, you know, a boat or a pontoon or something, you can say, oh, why is a pontoon more stable than a boat? Because it has these two big things on the outside. So if it tips a little bit, the center of buoyancy shifts really far. Whereas a boat, the center of buoyancy doesn't shift as dramatically when it tips a little bit. So a boat rocks more than a pontoon does. The last thing, if partially right, then these are the same magnitude but opposite directions. Okay. There's a lot more that we could do and say about kind of both of these things, but hopefully they give you at least some taste of some of the other stuff that's out there. At least a little feel for what some of this stuff is and what it looks like and how you can think about it. With that, though, we have 15 minutes-ish. So what we're going to do, if you have the paper that I had up here at the front, we're going to introduce the next section by looking at that. The goal of this basically is there's a super easy problem that you guys already know how to do without really thinking about it. So what we're going to try to do is force ourselves to think clearly about what we're doing, and then we'll take some of those concepts and apply it to things that we can't just like look at and know the answer. Okay, this is a lot of times, you guys know how to do this already without trying real hard. Try to force yourself to think through, what am I actually doing to answer this question? So kind of keep that in mind, and then we'll try to expand that and put a more rigorous mathematical framework around it. In the next section, basically, we're going to be starting to talk about what happened, how do we think about fluid flow and forces and things that are moving now instead of just things that are static. Yeah, so if you have that, pull that out, ask questions, talk amongst yourselves, and I'll be walking around. Okay, so yeah, just last enough. This is the last thing that we're going to do today. So whenever you're done with this, see you later. Happy Friday. But so you can stick around and work on it. When you're finished, you're welcome to turn it in and then have a good Friday.